All right. So today we're going to be talking about section 6.1. And in particular, we're going to be looking at something called area between curves. And so let's start with a what we know. All right. And so today's what we know involves a diagram. We've got this function. Maybe we'll highlight that function right there. All right. We've got this function f of x. And we have this area, right? So we're finding the area. That is this light blue situation. And we're starting at A and we're going to B. And I think we probably might remember that if we're looking for that area and we wanted to write it in symbols, we would say the integral from A to B of whatever that function is, dx, right? And so that part is whenever we have been finding all those numbers. So anytime we find a definite integral and we get this number at the end, what that number means. So let's say I did this integral, I got a 10 at the end. That would mean that the area of this shape is 10. Okay. Now, before we learned how to do the antiderivative and plug in the number, we also had this idea of sort of approximating things by rectangles, right? And so if we think back to our LRAM and our RRAM and our MRAM, and we were to sort of put some rectangles underneath this shape, we might see that we have something sort of like this. Okay, we would divide that up into a few different rectangles, as many as we wanted. The more rectangles, the better. And we would choose sort of whether we wanted to have a rectangle come from the left, like this, right? Or we had ones where we could come from the right. And then sometimes we thought about what happens if we could come from the middle of the rectangle. And I think a lot of folks noticed that if we chose sort of that midpoint and we split the difference, that we tended to get more accurate answers. But we were really focused on that process of like setting things up and how do we know if we're going to be coming from the left or coming from the right. And so that was sort of the overarching story of chapter 5, right? We were able to do a lot of computations, like all of this. We spent a lot of time finding numbers or finding equations, but at the end of the day, all we were doing is finding the area between the curve and the x-axis. And that's so important. I'm going to type it in here that the integral tells us about the area between the x-axis. Oops, let me rephrase that. Between the curve and the x-axis. Okay. Now, between the curve and the x-axis, you might be like, why does she keep saying this whole thing? Like, why can't I just say area? Why can't I say area under the curve? And I've chosen this phrase specifically because it's very precise, right? We are finding the area. What area? Well, the area between this green curve, and let me pick a different color, and the x-axis, right? The rectangle stopped at the x-axis. And so when we say we're finding this area, we're finding the area between whatever curve we have and the x-axis, all right? Now, if we remember the equation for the x-axis, right? If I were to write an equation down here for this, I would say that this is y. Let's call this g of x equals 0. Exactly, right? So we have this f of x, we have this g of x, but it turns out this whole time I've been keeping a secret from you. And the secret is this, because it's time to let that secret out. The secret is that, yes, we've been doing find that integral, you get the area. But what you've actually been doing is this: integral from a to b of f of x minus 0. Yeah. In other words, this whole time you've really been doing the integral from a to b of f of x minus g of x. We've just been looking at a very special case where g of x happens to be 0. And because it's 0, we never needed to write it. Okay. And that's why we had just this sort of simpler looking integral, right? Today, that is all going to change. All right. So you can celebrate, you can groan, you can cry, whatever it is that you feel like is appropriate reaction to this. But today that is going to change. All right. Because what we really want to do is in this what's new section. And in fact, we want to generalize what we do. We don't want to be tied to the only kinds of questions we can answer are when that x-axis happens to be the other function. All right. In fact, we want to see what we can do to generalize just finding area between curves. So now when we say we find the area, we're really saying find the area between two curves, and we are specific about what those two curves are. And so if we move over to the what's new picture, all right, you can see that in this first picture, we've still got an f of x, right? And we now have this g of x, and this g of x is not on the x-axis. So if we think about where we really started, right, f of x minus g of x, we can't just imagine that it's 0 and only have an f of x now. In fact, when we approach a question like this, where that second function is not the axis, we really want to say the integral from a to b of f of x minus g of x. Okay. So we're going to make sure that we have an idea of what that function is and an idea of what the second function is. And if you were to describe the relationship between the f of x and the g of x, one thing you might notice is that f of x is, where did my color go? F of x is the sort of, maybe we refer it to as the top function, whereas the g of x is something we might refer to as the bottom function. Right? And so I just want to take a moment and clarify what I mean here, top function and bottom function. So when I say top function, I literally mean that it is further away from the x-axis, right? So the x-axis is all the way down here. And if I were to start from the x-axis and go straight up, the second one that I get to is my top function. Okay. But if on my journey from the x-axis, I'm going up and I hit the first function, that function is my bottom function. Okay. But we are doing this from the x-axis and saying we are going up and counting up as positive. Oh, what if they're equally close to the x-axis? You mean like maybe we didn't have this green one up here, like if we had the other one right here, like right on top of g of x? Okay, so let's maybe try and draw a couple of these pictures to answer that question. So let's say we had one, and maybe we had like one here, and then we had another one here. I would say that the purple one would still be considered the bottom function, and the green one would still be considered the top function. Okay, and so yes, it can be relative to the x-axis, but also if you almost took away the x-axis and we just imagined the graphs like that, the one that is higher than the other one is considered our top function. Okay. If we, yeah, there we go. Cool. All right. So why is this important? And why in the world did we start our question about all of this with rectangles? Okay. And why have I been saying, I really need you to write dx. I need you to write dx next to every integral that you write. And if you don't have that dx, then that's not correct. Well, let's zoom into these other pictures here. Okay. So in this picture, they've shown us that they've sectioned off the A and B, right? We've got our starting point, our ending point, and they've drawn a few of these rectangles in that space. And if I look at just one rectangle, all right, any one of those rectangles, here's what I see. I see that this is maybe the y value of the top function, right? We happen to call it f of x, but whatever the top one is, it matters more whether it's top or bottom and less what the actual letter is for it, okay? But that means that this g of x sub I is the y value of the bottom function, okay? Now, why does that matter? Let's say that this y value for the purple one is, let's say 2. Okay, I'm just going to pick a random number. Let's say that it's 2. What could be a possible number for this y value of the green function? Yeah, maybe 5, maybe 4, right? But we know that it would be something that has a higher y value. So let's say maybe let's split the difference. We'll call it 4.5. Okay. If I asked you how tall this rectangle is, what would you tell me? How tall is that rectangle? 2.5, right? Yes, okay. And here's the structure I love. 4.5 minus 2, that tells you the height of the rectangle, right? So in other words, the height of this rectangle, so height equals 4.5 minus 2, or f of x minus g of x, right? Yeah, exactly. So we have 4.5 minus 2, we get f of x minus g of x, all right? So that sort of explains why up here I've said we're going to do f of x minus g of x, because when we take all these rectangles and we mark them off so they all have the same width, the same direction across the x-axis, right? And remember when we were doing the rectangular approximation and I said, we've got our area equals base. And then I said, I want us to write all the heights as like our, right? And I said, instead of finding the area of every single rectangle and adding it together, notice that that base is the same for all of them. So we could factor out that base to the front and then find all the other pieces. And at the time, it just seemed like this weird thing that Judy was asking us to do. Like, let's just bring this number to the front. And it's like, well, why would she want to do that? And here's why. Okay, here's why. This base, like the base of each of these rectangles, is something we call delta x, or it is the change in an x value. Okay. So delta is a Greek letter, right? So delta is a Greek letter. This is kind of silly, but what do you think is the corresponding letter in our alphabet for delta? Yeah, right? So delta in Greek is the same as the letter D in the alphabet that we use here. So now, instead of delta x, well, let's replace that delta with the letter we use. That dx that I've been like, I need you to write this at the end of every integral. If you don't write it, it's not correct. This dx, this dx, this dx. Anytime we've written dx, what we've really been writing is sort of the base of each of those rectangles, this base in particular, okay? Now here's the deal. We didn't give it a number, right? When we were doing rectangular approximation, we didn't give it a number. We gave it the number from the graph, right? But when we've been doing integrals, I just said write dx. And so why is it that when we do with rectangles, we have a number, but when we do with integrals, we don't have a number? And that goes back to, do you remember that Desmos activity where it was like split the region into 4 rectangles and then you could choose how many rectangles? Exactly, Matt. And some of the numbers in Desmos, you could put in like 1,000 rectangles, all right? 1,000 rectangles. So imagine if I took this space in between here and I tried to draw 1,000 rectangles, right? This is like a lot of rectangles, and that's not even like 100 rectangles. So you draw an infinite number of rectangles. What is the base of each rectangle? Exactly. Okay, if you sit and you draw an infinite number of rectangles, this base becomes so small. It becomes so small that basically what we end up doing is finding the height of a line. That's the f of x minus g of x. And for every rectangle, we do f of x minus g of x. And then we add up all of these lines. The dx tells us that we have an infinite number of rectangles. And this integral symbol tells us to add them all together. Okay, let me write that down over here. When we have our integral from a to b of f of x minus g of x, this dx is sort of the base of each infinitely thin rectangle. This squiggly symbol that I've been like, just write it, don't worry about it. It's a symbol, we need to know it. This means sum of all heights. In other words, we're taking our f of x minus g of x for every single rectangle, like a bazillion rectangles, and we're adding them all together. And this f of x minus g of x, that tells us how tall every single rectangle is, right? Here, I said this is 4.5 and the bottom one is 2. So then the height of this rectangle is the difference, 2.5. But if the height of the top rectangle, like the y value is, let's say 10, and the y value on the bottom is 2, what is the height of that rectangle?
8.
8, exactly. And it doesn't matter. Like, it does not matter which way we have our rectangles. All right, like it doesn't matter how many of them we have. It doesn't matter where that rectangle is. But at the end of the day, every single rectangle, we can find the height by saying top function minus bottom function. And so that is really the beauty in all that we've been doing. All right, there's been this backstory here this whole time, and we just haven't really talked about it. We focused more on what to do, but we haven't talked about why we're doing it. Okay. And so with that, what we're going to do is do a little bit of a summary. All right, we're going to do a little bit of a summary. We're going to do some problems. We'll do some calculations, but most of our calculations, I think we might leave for you to finish on your own time. Mostly because I think learning how to do the setup piece is going to be the most important part. Okay. All right. So you'll notice that pretty much every problem we've done has been something, something, something dx, something, something, something dx. Like we've always had a dx at the end. And one thing I want to sort of put a bug in your ear about is that when we say with respect to x, that means at the end of our integral, we're going to see a dx. Exactly. In contrast, if I wanted to do something with respect to y, I would have a dy at the end. Okay. We're going to leave the dy for a little bit, but I want us to fill in some information about the dx part. Okay. So a few important things to maybe write down about dx. Right. Rectangles in this situation will be, I'm going to use that symbol. Anybody remember what that symbol means?
Perpendicular.
All right, so rectangles will be perpendicular to the x-axis. Right, so all of our rectangles will be perpendicular to the x-axis. And if we look back up here, we see that our rectangles are like this, and they are perpendicular to the x-axis, right? The heights of the rectangles go up and down, but the x-axis goes side to side. Right, so one thing to keep in mind, rectangles will be perpendicular to the x-axis. All right. Now I do want to put a warning out there. A lot of what we're going to do in this last week requires you to draw things. So I'm going to encourage you to be really paying attention to how we draw things and why things are a certain way, okay? So rectangles are perpendicular to the x-axis. We generalize this formula for area where we said we could say the area is the integral from A to B of, I'm going to say, the top function minus the bottom function, dx, okay? And so again, this gives sort of the base of every super skinny integral or super skinny rectangle. This part gives you the height, right? So we have base times height, but we want to add up every single one of these tiny rectangles starting at A and ending at B, okay? I want to write down two more things here, all right? A and B are x values, right? Now, these are things that we have sort of assumed to be true, and up until now, it's always been the case, all right? But especially, I think after today's lesson, I would encourage you to just go back and make sure you understand the reasoning of why we're choosing these. Because if you're just going to try and gut it out and memorize it, next week might be your worst nightmare, okay? I don't want that for you. I would love for you to finish off 150 feeling really good about things, okay? But a lot of that foundation is in this section in 6.1, okay? So A and B are x values. And I want to tell you about one clue that I typically look for to know whether I should set something up with respect to x. All right, and so we'll say that we are typically given equations, I'm going to say functions. We're typically given functions that are f of x or g of x or whatever letter we want, but the variable in the equation is the x, all right? So in other words, y equals something with x, okay? All right, so let's keep this here, okay, for a moment. We're gonna do a couple examples. And then after break, we're gonna come back and take a look at this with respect to y part, okay? Let's do a couple examples, keeping these four clues in mind, all right? Our rectangles are gonna be perpendicular to the x-axis. We can say that the area is gonna be the integral from A to B of the top function minus the bottom function. A and B are x values. And in line with what we've been talking about with u sub, if these are x values, my equations should have x's in them, right? Which makes sense that we should have something with x. All right, so let's draw some pictures, all right? There will be lots of drawing on exam 4. There is some drawing on some of the homework that you have to do this week as well. All right. So a typical question looks something like this. Find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. And so what I like to do is I like to start by, surprise, surprise, drawing a picture. I like to start with a diagram. And I will be asking you to start with a diagram, okay? After that, I like to find intersection point. Okay. And I'm going to put a star next to this one because for some questions, we might have to do this, and for others, we might not have to do this. Okay. But it is a skill that I would practice to make sure that you know how to find the intersection points in case you need to do so. Okay. Now, this is where we start to think back to all of the different types of graphs we learned and think about what their shapes are, even if we don't know what exactly they look like, we should know a general shape, okay? And so in looking at this, I have y equals x squared and y equals 2x minus x squared. And so you'll notice that it doesn't say f of x, it doesn't say g of x. It just gives us two functions, and we're supposed to sketch a picture for these, okay? And so we have y equals x squared. We might realize that this is our very classic parabola, right? Just a parabola facing up. I'm wondering if you can tell me what the x-intercepts of this parabola are. Good, 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 good. Okay, so we know that x-intercept is at 0, okay? All right, let's take a look at the second one though, y equals 2x minus x squared. Tell me about that parabola. What do we know about that parabola? It is downward facing, good. And what are the x-intercepts for this parabola? How did you know that? All right, all right. So if we were to take this and rewrite it, we could factor out an x, and then we would have 2 minus x, right? And what's true about all x-intercepts? Well, all x-intercepts have a y value that is 0. And so we can see from here that x equals 0 will make this true, and x equals 2 will make this true, okay? And so knowing that, let's go ahead and sketch a graph, okay? Now, here's the uncomfortable part. I know we have Desmos. I know we have access to technology, right? Why wouldn't we just draw that on there and call it a day? And I think it really depends on how far you plan to go. If you plan to be a math major, this is the kind of stuff that you need to know, okay? If you're not there yet, I would encourage you to take some time over the next month, maybe before school starts again, and make sure you know how to do these things, okay? The thing about the higher level math is you draw upon a lot of the procedures that you learned in the past, but you use them in different ways, okay? So when you first learned about drawing graphs, it was just about drawing the graphs, but now it is the first step in a longer problem, okay? And similarly, like if you look at U sub, what we learned the last couple of days, U sub eventually is going to be the small end piece to a problem. It won't be the whole problem. It'll be a part of the procedure, okay? If this is the end of the road for you in terms of math, then maybe it's a little bit less important, right? But even if you're going to be going into, I don't know, computer science is always a little bit different of a beast, but a lot of these, you know, if you're going to do anything in engineering, you really want to make sure you know some of these foundational pieces, okay? This is almost like one of the last moments in your math career where it's still going to be okay to not be super aware of these things, but that drops off really quickly once you start to take a lot of the higher level classes, okay? And I don't say that to scare you. I say that to help you understand what you might need to do to be a little bit more prepared, okay? Anyway, let's go ahead and draw this graph. All right. So I've got this parabola, this upward facing parabola. And I notice that this upward facing parabola has an x-intercept of 0. And so maybe it looks something like this. Okay. And then we have this downward facing parabola, 2x minus x squared. I know it crosses at 0. I know it crosses again at 2. And so maybe it looks something like this. Right? So we've got this graph. We have our two functions. And the question says find the area of the region bounded by this. That means the area they're looking for is this sort of like piece right here. Kind of looks like a flower petal, right? This little piece is what we're going to find the area of, okay? Now, we're going to add to this diagram, okay? So when I say diagram, I don't mean just copy from Desmos and draw or sketch it out, okay? You're right, Matt, we need to know where they cross, but we're also going to set up a few other things, okay? So for example, I know this coordinate is 0, 0, where they cross the first time. Any guesses as to where they happen to cross the second time? Sometimes we can sort of guess a little bit based on the equation.
0, 2.
0, 2 is over here, but that doesn't look like the purple and the green cross, right? So we're not looking for x-intercepts, but maybe this point is at 1. Well, if they cross at 1, like x equals 1, what's the y value there? Yeah, because we could plug it into the purple equation or the green equation and find the y value that goes with it. Okay, now I would say this is a really good guess. It happens to be correct. But as we move forward, we're going to find that those intersection points might be a little bit less nice. All right, that's why there's a separate section that says find the intersection points, because I want us to know how to do that algebraically. Okay, it's not about computing things, it's about understanding a process for how to find where things are equal that you'll see again in a lot of other classes. Okay, now there's one last thing. Excuse me, there's one last thing that I would like you to draw in your diagram. Okay, I will be looking for this in your diagrams. So if you have any classmates who are not here today and don't regularly watch the videos, please tell them that this part must be in your diagram. Okay, you draw this is not 100%. Here's the last piece that I want in these diagrams. Okay, the reason I want them is because if we learn how to draw the rectangles now, next week will be easier for you. Okay, so we're paying it forward. We're setting up a structure that works for more than one situation. I'm going to go back to this diagram. And if we look at our equations right quick, we've got y equals x squared, y equals 2x minus x squared. Well, that sure looks like a y equals something with x kind of equation, which is our clue that we're going to be setting up our integral like this. So that means that our rectangles will be perpendicular to the x-axis. So the finishing touch for your diagram, I would like you to draw some rectangles, but we're not going to draw them as rectangles. We're going to draw them as super skinny rectangles. So like this. You see how that is like our f of x minus g of x, but like very, very skinny. In fact, only the width of your pen, pencil, writing instrument. That right there is an example of one of the rectangles in this shape. I could draw another one. Maybe there's one here. How many rectangles are there between the two rectangles that I just drew? There's infinitely many, exactly. Okay, now, Matt, you ask a really valid question. If you shade it in, it's like the same thing, right? Here's the danger in the shading. Right now, our rectangles are vertical. They're perpendicular to the x-axis. That's going to help us set up our equation. But let's say we encounter a situation where the rectangles go the other way, like perpendicular to the y-axis, we would set up our equation a different way, right? And so when you shade it in, right, you're like coloring and it's also pretty. If you shade it in, you actually lose the fact that one is perpendicular to the x-axis and the other is perpendicular to the y-axis, okay? So that's why I usually tell students, don't shade, draw rectangles, draw some lines, make sure you know which direction those lines are going, okay? So if I wanted to, I could draw a few more. Maybe I draw this one, maybe I draw a little baby one at the end, or the little one down here. It doesn't matter how many you draw. You could just draw one, maybe two, you could draw five, I don't care. But I do want you to show me you understand that this picture and this equation is almost begging us to use with respect to x, okay? Now, let me ask you a question. These rectangles that we just drew, they are they A, stacking along the x-axis, or B, stacking along the y-axis? Good question. So by stacking, I mean like they're sort of lined up this way, right? And they are lined up along the x-axis. Does that make more sense? Okay. I'm going to actually write that here, that the rectangles are stacking along the x-axis.
Could it be along the y-axis in another case?
Yes, in a different case, if you draw your rectangles differently, like if your rectangles went this way, then you would say the rectangles are stacking along the y-axis.
Does it depend on me or of the problem?
It depends on a lot of different things, and I'll try and make that clear as we go along, okay? All right, so we've got our diagram. It is very dense. You've got your graphs, you have your intersection points, you've identified, I mean, sort of, I snuck it in there, like which one's the top function, which one's the bottom function, and you've drawn some sample rectangles, okay? So this next piece, let's kind of confirm for ourselves that the intersection point that we guessed is actually true, okay? So in general, if I want to find where two functions intersect, all right, so to find where two functions intersect, set them equal to each other. All right, so to find where two functions intersect, set them equal to each other. All right. In other words, we can say that x squared, the purple one, is equal to 2x minus x squared, the green one. All right, so we could say x squared equals 2x minus x squared. And in terms of a solving strategy, I see some quadratics, and so my gut instinct, my process that I'm saying, okay, I should do this, is we are going to move everything to one side, set it equal to 0, and then we can do what Matt said, which is factor. Okay, so we're going to move everything to one side, we're going to set it equal to 0, and then we're going to factor. So I'm going to add the x squared, so I'll get 2x squared. I'm going to subtract the 2x, so minus 2x equals 0. Right? And now we're going to factor. So 2x, x minus 1 equals 0. And I'm going to get x equals 0 and x equals 1. Okay. And that means that our guess up here for it being 1 was actually correct. Okay. Now, maybe you knew that because my diagram is so beautiful that you knew that this is 0, this is 2, and this one happens to be halfway in between, right? But we don't always know that. Maybe it's going to be like 0.95 or, something close to 1. So this idea is important. Like if I want to know where two functions intersect, that means they have to have the same x and y value at that point. And that's why we set them equal to each other. Well, if you don't move everything to one side, you might be missing a solution. Okay, so I don't know if that's what you're asking, Abby, but it would be really important to move everything to one side before you start dividing. If you divide at this point, you're going to lose that x equals 0 solution. While I'm waiting for your response, Lucas says, should we find intersection points first and then do the diagram, or is the diagram a guess? You can almost do them together. Some people like to find the intersection points and then sketch the diagram. So the order here is actually not as important. So if you feel comfortable finding the intersection points first so that you can draw it more accurately, that's fine. Okay. So Abby, I'm not quite sure what you mean by if you set them equal to each other, they only equal 1. I'm wondering if you can clarify that. Oh, and thank you, Matt. I've drawn this diagram a lot. It doesn't always come out well, but I think the tablet helps instead of on the board. Board work it's colorful, but it's not always very well done well. What do you mean by they only equal 1? I think that's the part I'm confused about. So this is a negative x squared, right? So when we add it to the other side, we don't get, like the x squareds don't cancel each other, we get a 2x squared. Okay, so let's write this out. So 2x squared equals 2x. Is that what you mean?
Sorry, maybe I should just talk, but yeah, that's what I mean.
Okay, and then did you divide by x or 2x?
Yes.
Ah, okay.
Mm-hmm.
So this is where you're gonna lose solutions, okay? So let's see what happens. I divide by 2x, right? So I divide by 2x, I divide by 2x, I get x equals 1. That's all fine and good, but from our picture, we can tell there's another point, right? So here's what happens. When you divide by 2x, you lose this solution. And so in general, when we see any sort of like quadratic equation, we want to move all the terms to one side and set it equal to 0. This minimizes and actually eliminates any lost solutions. Yeah. Okay. Now, this was something that is maybe a little less important in your younger years, right? In your previous math classes, maybe this didn't matter. But now that we're saying, I want to find where these two curves are equal to each other and you only get 1 point, right? That makes it a lot less, or it makes it a lot more important that we move everything to one side and set it equal to 0. Okay, thank you for being that guinea pig. I was thinking you did this, and this is a super common misconception, right? Because it's like a shortcut. Like, I don't have to factor. I can just keep everything on both sides. So why wouldn't I do that? And it is this reason right here where you lose a solution that we don't want to do that. Okay. All right, so let's go ahead. So we've done the diagram, we've done the find the intersection points, and now we're going to actually set up and solve our integral. Okay. Yeah, in general, when we see x squared, we know that there's going to be 2 factors exactly. All right, so now we are going to set up and solve the integral. Okay. All right, so this is our very first problem. And so what I'm going to do is say, write down the equation. Area equals the integral from a to b of the top function minus the bottom function dx. All right, and now we know all of those pieces in that equation actually tell us something different. So if we leave one part out, we're not being very thorough in what we're saying. But this is the glorious part. All this work that we've done to set things up, our pre-thinking has actually given us all the information to set up and solve our integral. Right? In fact, I bet you can tell me what A and B are. Right? Looking at our diagram, A to B. Right? A to B. Now, in some ways, I love this problem because the computations aren't too hard, but the one downfall to this question, I think, is that the x and y values here are the same, and the x and y values here are the same. So I want to be really explicit about which one you are using. Earlier, we said if our rectangles are stacking along the x-axis, we want to choose the x values as our A and B, okay? It is so important we use the right value. If we have a bunch of x's in our equation, our bounds should also be x, okay? Think about this as like your most type A OCD person in your life. That could be you, I don't know, but who is that person, and like how much would it bother them if things didn't match up exactly? That's really like where a lot of this mathematics comes from, right? Like everything is built on something else, so it all has to fit together, otherwise the universe falls apart. Okay, so we're going to choose our 0 as the bottom bound, our 1 as our B value, because those are the red highlighted X values of our intersection points. Okay. Now, our top function, I sort of color coded right off the bat, but it's okay if you didn't know. You can just draw them in regular and then color over them if you want. But our green function, the 2x minus x squared, is the top function, and our x squared, the purple one, is the bottom function. And so we just want to do this. 2x minus x squared minus x squared dx. Yeah, I just zoomed in and out a lot. Let me zoom in at this picture a little bit better. Okay, so we can take a look at that. So if we zoom in even more, we see that this is like at the top of all of the rectangles. The green one is at the top of all the rectangles, whereas the purple one is on the bottom of all the rectangles. Yes, yes. And that is such a key point, right? Because I didn't even talk about that. Over here, you're right. The purple one is on top of the green one, but it's not in the interval that we're looking at. Okay, so I'm so glad that you clarified that. In the interval that we're looking at, we want to see which one is on the top and which one is on the bottom. Okay. All right. Yes, exactly, exactly. Says the region enclosed by the parabola. Perfect. All right, so let's go ahead and actually solve this one so we can walk through one that we fully solved. And then I think it'll be a good time to take a break and then come back and see how different cases work. All right, but you folks are on fire today. You were asking all of the right questions. So I think it'll be a good day. All right. All right, so 0 to 1. I'm going to go ahead and get rid of the parentheses. These parentheses have a plus sign in front, so I can just get rid of them. This second set has a minus, so I need to make sure I distribute that minus sign. 2x minus x squared dx, which simplifies to 2x minus 2x squared. If this is not one of the easiest integrals that you've seen in the last few days, I don't know what is. Okay, we've seen a lot. Pretty much everything we worked with this week has had to do with U sub, right? U sub, some really gross looking integrals. This is just asking us to use power rule, okay? And intentionally so, because a lot of the rest of the work we did is so much more thinking than than we did in the other problems. So let's go ahead and integrate, all right? What is the integral of 2x? Well, x squared. What is the integral of 2x squared? So 2x cubed over 3. We're going to draw that little vertical line. 1, put a 0. Okay. All right, let's plug in our bounds. 1 squared minus 2 times 1 cubed over 3 minus 0 squared minus 2 times 0 cubed over 3. This goes to 0, this goes to 0. So I end up with 1 minus 2/3. And we get an area of 1/3. Okay. So let's get that all on one page. All right, so the area of that little sliver is 1/3. All right, and in order to find that, we had to draw a diagram. Consider, are we going to do dx or dy? We found some intersection points because it was the region enclosed by it. And then we plug that into our area formula, making sure that we picked the right functions, put them in the correct place, had the correct bounds, and then the rest is all the skills we developed in chapter 5, right? All of this is from chapter 5. Now we're just putting it in a context, an application, all right? So this was a lot of thinking, right? A lot of thinking, a lot of setup, and we want to, I think, take a well-deserved break right now. Okay, so let me go ahead and stop the recording. All right, so before break, we sort of updated our story about, come on, there we go. We updated our story. Hold on. Okay, there we go. We updated our story to really kind of think about what we've been doing, why we have these certain pieces of this setup, like the integral expression, why all those pieces are so important, and how we can generalize that away from saying we can only do things when we find out where the x-axis is, right? And so we introduced this idea of having a top function and a bottom function, and talked about in particular how if we have our rectangles, well, let me do that again, our rectangles this way, that we can just find the height of that rectangle by saying top y value minus the bottom y value. And if we generalize that for all of the rectangles, essentially what we have is this top function minus the bottom function. We did an example, and this example was based on this idea of sometimes we integrate with respect to x. And so that is what we mean when we have that dx at the end of our expression. But we will encounter some cases where we have something, something, something dy. And so I wanted to take some time to unpack what that might look like and how we might know, like what are some clues we can look for, okay? And so what we're going to do is these 4 statements that we wrote earlier for with respect to x, we're going to take them and we're going to modify them for with respect to y, okay? And so let's start with this first one. So I said originally that rectangles will be perpendicular to the x-axis if we're looking at the x. And so it might be fairly logical for us to think now that rectangles, when we draw them on our diagram, the rectangles will be perpendicular to the y-axis, right? Now, when we draw the rectangles, they will be sort of horizontal in nature, and they will be, in fact, perpendicular to that y-axis, okay? Now, it turns out that when we're modifying this second one, area equals the integral from a to b of the top function minus the bottom function. Yeah, we're gonna say area equals, and we're going to use some different letters here. So A and B we typically reserve for x values, and then with no other reason than C and D come after A and B, we usually call the bounds of something with respect to y, C and D. And instead of having a top function minus the bottom function, we actually have a right function minus the left function. Seal that off with a dy, okay? So there you can sort of compare the two of them. With respect to x is going to be the integral from a to b of top minus bottom dx. But if it's with respect to y, we're going to say integral from c to d of right function minus left function dy. And as we made it explicit over for the dx, we said a and b are x values. it would be good to note that C and D are y values. Okay. So again, this is us imagining that most OCD or most pay attention to detail kind of person in our life, that everything needs to match, right? If we're going to be using dx, everything better have x's. And if we're going to do something dy, everything better have dy's. And if we revisit that idea of u sub, if we're going to do something du, everything should be in u land, okay? And so the last thing I want to modify is the statement, typically given functions that are f of x or g of x or h of x, y equals something, something, something. But in our with respect to y, we're going to be typically given functions that are something like, whoa, that are f of y or g of y or h of y, whatever letters you want to use. But really, instead of saying y equals something with x, we're going to say x equals something with y. Okay. And so let's keep this in our brains, and we're going to skip a bunch of examples. Well, we'll come back to them, but we're going to go all the way down to, let's see which one is most classic. Let's go all the way down to example number 8. All right, we're going to go all the way down to example number 8. We're going to take a look at that, keeping in mind what we just wrote down here about things that are with respect to y. So, so far down here. Okay. So, example 8 says, find the area of the region bounded by the curves. And so earlier, someone pointed out that word enclosed by, and the word bounded is another way of saying enclosed by, okay? And so when we're looking for that right function and a left function, we want to make sure we're looking in the region that we are interested in, right? So not just everywhere, but in the interval that we're interested in, which function is on the left, or which function is on the right, okay? Now, I do want to point out something here. So we read this and we say x equals -9 plus y squared and x equals 7y minus y squared. Now, we might look at these and say, I don't know how to graph that. And that would be a lot more reasonable, because I think in our math education, we spend so much time saying y equals, y equals, y equals, that it feels a little weird to say x equals, x equals, x equals. But a lot of those patterns that we know are still the same. Okay, so for example, I might go in here and write this as x equals y squared minus 9, right? That's the same thing as -9 plus y squared. Now, if the x and y were switched, I would know this is a parabola. What does that -9 do in terms of the graph? Anybody know what that -9 does?
Shift it to the right.
In a right, like let's say we had y equals x squared minus 9. Like, what does that -9 do? Yeah, that -9, okay, which I honestly feel like this is, if this were a bigger part of our curriculum, it would be really helpful. But this -9 in the y equals world means you move something down 9. Okay, so over here, I've sort of switched my x's and y's. We are going to have a parabola because it's y squared, it's going to be a sideways parabola. And this -9 exactly will move the graph 9 units in our quote unquote negative direction when we're thinking about sideways things, right? So it's a sideways parabola. We're going to move it 9 units to the left. What about this other one? Well, I know that it is some sort of parabola because it's like a negative y squared, but I bet that negative means that my parabola actually looks like this. So it's sort of facing the other way. And I might not know exactly what the 7y does, but I bet we could take a page out of our process from before and go ahead and factor that out. Because if nothing else, we can tell where that parabola is going to intersect the x-axis, or not the x-axis, the y-axis, okay? Yeah, so we can tell here that the y-intercepts will be 0 and 7, okay? So yes, these are not functions, all right? So maybe we call them graphs or we call them equations. They are not technically functions exactly because of what Matt said, that vertical line test, okay? So if we're thinking about our graph for these, all right, if we're thinking about our graph for these, everything is gonna be sort of sideways looking, and that's okay, right? That's okay. So we're gonna start with these two pieces, diagram and intersection points, right? Now, I think someone brought up a great point earlier, like, do we have to draw the graph first and then find the intersection points? And the reality is you can do sort of both at the same time if you want to. But the process, the idea of finding the intersection points actually is the same, even though this is like a bunch of equations with y in them, right? And it boils down to that idea that I can take one of the equations and I can set it equal to the other equation. And I know that might feel weird for us because we have y's in our equation and not x's, but what this is going to give us is the y values of where these two graphs intersect, okay? And so this is a good reminder that whenever we see the quadratics, we want to think, move everything to one side, set it equal to 0, and solve. And so I'm going to move everything to the left-hand side, and I'm going to get 2y squared minus 7y minus 9 equals 0. And then I'm going to factor. And I believe this factors into 2y minus 9 and y plus 1. Which means that these two equations will intersect when y equals -1 and y equals 9/2, okay? And so if for you it feels more comfortable to work out the intersection points first and then graph it, that's fine, right? I think it does make the graph a little bit more accurate. Let's see how this one goes. All right. So, I'm going to do this. I'm going to draw this x equals -9 plus y squared in purple. And I'll do this x equals 7y minus y squared in green, okay? So the purple one, I know I have a sideways parabola, and all I'm going to do is take that sideways parabola and sort of bring it 9 units to the left. And so we might end up with something like this. Okay. Opening to the right. So just like by default, when we're looking at like an X situation, positive means up. When we're looking at something with Y, positive means to the right, okay? So we've got this parabola, and then we've got this other one, 7y minus y squared, that actually opens in the opposite direction. And in fact, I know it goes through 0 and 7, which I think is up here somewhere. And so we'll end up with something kind of, oh no, something kind of like that. Okay. And so let's write down those intersection points here. I know that this intersection point, I don't know what the X value is, but I know the Y value is 9/2. And down here, I don't know what the X value is, but I know the Y value is -1. Okay. All right, now we know, because I made a big deal of it earlier, that this diagram is not done. The diagram is not done because we haven't drawn in our sample rectangle, right? And the number of sample rectangles that you choose to draw is up to you. But we want to make sure in looking at this that look at all these clues, right? This is an equation that has like y's in it, y's in it. I was able to find the y values of the intersection points. And this graph kind of looks like sideways almost from what we were looking at before. That means that my rectangles are going to be perpendicular to the y-axis. Exactly. They are, in fact, going to stack, or I can't remember the other word I used, but they're going to stack or line up along the y-axis, right? So for example, this might be a rectangle. This might be a rectangle. Maybe there's this one, but there's like a tiny one down here, right? But those four, if you visualize them sort of like animating, they're going to be stacking up the y-axis, okay? And so if we write that out, we can say rectangles are stacking or lining up along the y-axis, okay? And I think it was Evelina who pointed that out earlier, that sometimes, like, why do we have to write that down? This is the sort of why we're writing it down, because sometimes they're actually stacking in a different direction, okay? So let me pause here for a moment, all right? So I've done a lot of talking in terms of like, here's our diagram, here's our setup. Are there any questions here before we set up our integral? Because we're not going to solve this one, but we are going to go ahead and set it up. Okay, great questions here. So let's see. I think we'll answer the first question. Do we need to find the x values first as we set up our integral? Okay. And the second question, you look at these equations, right? You could take this equation. Didn't leave myself enough room. I could say x plus 9 and the square root of that equals y. Two things. You would, one, need plus minus. You would need like two separate functions. If you only did plus, you would get like the top half of the parabola, but not the bottom half. The second thing is, we know that we're going to be integrating. And we know that we're going to be integrating because it asks us to find the area. And I don't know about you, but I would rather not integrate like with the square root situation that might need use of. Whereas look at the way this is written. If I wanted to integrate this, it's power rule all the way, right? Same thing over here, 7y minus y squared, power rule all the way. So if it were a computer doing this, maybe it doesn't matter as much. But if we're going to engage in this process and compute things, we would really like to set ourselves up for success and sort of choose the most efficient way to do things. Okay. And I think that's sort of like this misunderstanding of like what makes people good at math. Sometimes we think that people who sort of can compute the fastest are good at math. But I think the reality is the people who can choose the most efficient method, meaning they have a lot of methods to choose from and they know which one might be easier. They can almost think like a few steps ahead. Those are really important skills to cultivate, okay? Because I think those actually lead to being able to compute things really quickly, all right? But I'm so glad you asked that question. I think after this question, we'll go back and see one where maybe we could have done either way. And I think that's sort of the tricky part. So you do have a little bit of choice occasionally, but some are very classic dx and some are very classic dy, okay? So let's set up and solve this integral. And you know I like to write out that formula and make sure that I'm matching everything in the right place. Okay, so integral of c to d, right minus left dy. So we'll get the integral of, now these c and d we said earlier are y values, right? Because we have a dy at the end. All of the equations we're going to be using have y's in them. So our bounds should also be y value, okay? Now I agree. I think that one of our bounds is the -1. I think the other one is 9/2. But just like we typically start, like if we're doing dx, we typically start here and go this way, right? When we're doing dy, we typically start at the bottom and sort of stack up, okay? So we would choose the smaller y value, -1, and we would end with the higher y value of 9/2. Now, again, I sort of preemptively color coded the graphs, right? But after you draw them, you can always draw them and then go back and color code them. So the one on the, which function in this interval is the one on the right? And we can almost use the rectangles we drew to answer that. If you go to one of your rectangles, you can say which function is on the right, which function is on the left. And it turns out that the green one is the one on the right and the purple one is the one on the left. So we can say 7y minus y squared minus -9 plus y squared. All right. Now, if you've been with me all summer, you know I try and write more symbols rather than less. I try and put in these symbols because I know that I'm going to make mistakes. And I know some of you are also going to make those mistakes, right? So I want to put these parentheses here because this minus sign, it has to be distributed here. If you don't distribute here, it's not just a sign mistake. Your whole area is going to be wrong. And that's such a silly reason for it to be wrong. Look at how much good work you did, right? Don't blow it because you were too lazy to write those parentheses, okay? So it isn't that I want you to write more. I mean, I do, but the reason behind that is because I think it prevents a lot of mistakes, all right? And we're headed into the last week. I'm gonna feel a lot less bad for you if you make those mistakes than I would have during week 1, okay? So we set up our -1 to 9/2. We get 7y minus y squared plus 9 minus y squared. And we'll end up taking the integral of -2y squared plus 7y plus 9 dy. And all of that is power rule all the way. All right, power rule, power rule, power rule. Plug in the 9/2, plug in the -1. And at the end, you should end up with this, okay? So the computation involved in getting from that last line that we wrote to the answer, all right, this is that level of computation is not necessarily something I would ask on an exam. I think that's a lot of not so very nice numbers that sort of almost makes the rest of all that thinking that you did feel less important because you're like cranking through some numbers. But what I'm really interested in is, can you draw a diagram? Can you find the intersection point? Can you set up the integrals? And if it happens to be nicer numbers, like we'd had in the first example we did, where it just ended up being like 1 minus 2/3, sure, that would be fine. That would be something I would want you to be able to compute, all right? But 1,331 over 24, I don't really see a benefit in asking you to do that part by hand, okay? So how are we feeling after seeing one example for dx and one example of dy? Let's see, I have a couple questions here. Okay, so I have a great question in the chat about, does it matter which one you choose as right or left, or if you could just take the difference and take the absolute value? And I think that it becomes a little trickier to take absolute value at the end. The reason being, some of that area might be positive, some of it might be negative. And when you absolute value, you're only changing the negative part to a positive. So it is potentially possible that you could almost double count some of that area doing the absolute value. So I would make sure to maybe not do that, right? And instead to think about which one's on the right and which one's on the left. That's sort of one reason. The other reason is next week, it will also be very important to be able to identify right curve and left curve, because we're going to use that in the context of a different problem. So we're really practicing some identification strategies here that we're going to use again next week. All right, so I see some feeling good so far. All right, so let's see, which one might be a good one to choose? Okay, so I think from here, what we're going to do is we're going to take a look at example 6, okay? But before we go to example 6, I want to look at the diagrams from 8 and 1 again more carefully. Okay, so this diagram right here, all right, we look at the rectangles that we drew, and we said, oh, let's find out the right and the left curve. So I want to ask you something. For this blue rectangle right here, which curve is on the right, the green one or the purple one? The green one. Yeah, the green one is on the right. Okay. What if I chose this one? Which curve is on the right? Still green. What if I chose this one? Which one's on the right? All right, what if I chose this little baby one down here? Which one's on the right? The green one. Okay. And if I went back through and I said which one's on the left, for every single one of these rectangles, you would say that the purple one is on the left, right? So here's one thing. In this diagram, in the interval we are looking at, every rectangle in that area has the same right curve and the same left curve, okay? Let's go back to example number 1. Oop. With my tiny, tiny diagram here. And let's ask ourselves a slightly different question. So this rectangle right here, which curve is on the top? Green. Good. Every single one of these rectangles that I draw in that interval has the green curve on top. Okay. We're going to take a look at example 6 because that one gives us a little bit more to think about. Okay. Okay. So example 6 looks like this. Find the area of the region between these curves. Y equals 20 minus x, y equals square root of x, and y equals 1. And so we're going to start with a diagram. We're going to find some intersection points, and then we'll see where that takes us. Diagram. All right, I see another question in the chat. The area of the left of the y-axis considered negative area? Yes, it is if your right curve is the y-axis. But if you're looking at between two functions, if you set up right minus left, it will come out as negative, right? Because you'll have 0 minus something and it'll come out negative. That's a great question. All right, we've got a little bit different case here right now. We've got 3 functions, and that's not something that we've seen yet. Okay, so I'm going to go ahead and take a look at these functions. So let's go ahead and start with this one. I think that's a nice, straightforward one. What does that look like? Y equals 1. Yeah, it is a line at y equals 1, and more specifically, it is a horizontal line at y equals 1. Okay. All right, let's go to maybe this one. Oh gosh. Let's go to this one. Y equals 20 minus x. What does that look like? Good. Y-intercept at 20 and a slope of -1. Okay, so maybe that looks something like this. Okay. And let's choose a different shade of green. Tell me about that y equals square root of x. What does that look like? Yep, sideways parabola, but just the top half. Okay. So we have 3 functions this time. And from the equations, right, I have y equals 20 minus x, y equals square root of x, y equals 1. Would you guess that we're doing dx or dy?
X.
Exactly, dx, because everything has x's in the equation part, right? So which direction should we draw our rectangles? Would they go stacking along the x-axis or stacking along the y-axis?
X.
And so that might look something like this, right? Here's one, here's another one, here's another one, here's a little itty bitty one. Okay. Now, I'm going to ask you the same questions I asked you earlier, right? Here's this rectangle. Which function is on the top? Light green, dark green. That's square root of x. Dark green one is on top. All right, let's move along. What about this rectangle? Which function's on top? Dark. Good. Let's skip a few. What about this one?
Light.
Light. Good. What about this? Yeah, that 20 minus x. Well, shoot, how am I supposed to write an equation if sometimes some of the rectangles have the dark green as the top function, and then other times we have the light green one? Okay. It turns out that we can do exactly what folks are saying in the chat. We need to set up not one, but 2 different integrals. All right. And so here's what we're going to do. We're going to find the intersection points, but we are now going to have to find 3 of them. And in particular, we're going to find this one, we're going to find this one, and we're going to find this one. Okay. Do not be overwhelmed. All right. We're just going to take that process that we looked at earlier, and we're going to sort of expand upon it. So the first thing I want to do, find the intersection of this dark green and the purple. If I want to do that, I have to take the dark green equation and the purple equation exactly to each other, okay? So we get square root of x equals 1, and that means that x equals 1, right? Now, wonderful question asked earlier, which was, we need to find part of the coordinate, like meaning I have an value. Do I need to find the y value? And I would say hold off on that until you know that you need to find it, okay? So I'm just going to take this point and I'm going to label it as 1 comma something. And we can find that something if we want to. All right, what if I want to find this second intersection point here? Set the dark green equal to the light green. Good. So 20 minus x equals square root of x. All right. What I would do here, if I were to solve this algebraically, I would square both sides, meaning 20 minus x squared equals x. I would FOIL out, and then lone x to the same side as the other stuff. So 400 minus 40x minus x squared equals x, or let's see, x squared plus 41x, is that right? Plus, nope, 400 equals 0. Let's see, x squared plus 41 minus, yeah, I think that's right. Okay. Wasn't this? Oh, loop the 40x to the right hand side, because I didn't want my x negative, so I just moved all the terms to the right hand side. Yeah. So now we factor. Right. I'm gonna labor this point, but a positive value and then I think a negative value, right? We want to think about numbers, try to make negative 400, but add to make a positive 400. So I think it's like negative 16, 400 divided by 16. I don't even know. 25. Does that work out? That doesn't work out. Something wrong there. 400 minus da, 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 da. Yeah, but we will get that positive 41 there in the middle. Hmm. X squared minus 41x plus 400. Oh, they're both positive. It's a plus 400. No. What did I do wrong? I think I made a sign mistake, so I'm not working out the way I wanted. Oh yeah, you're right. Great. Well, so I could model for you today. It's like to not be able to find a mistake. All right, so that is the plus sign, right? Because the negative x squared or negative x gives us a positive x. Okay, so then I actually have a negative 41x and a positive 400. And that makes sense that we have negative 25 and negative 16. Awesome, thank you. So we end up with x equals 16 or x equals 25. Now this is a little tricky because like, how do you know which one of those is going to be correct? And so I think it's going to be useful to go ahead and find that third point, because that will probably be one of these, the x point. Okay. So for the third intersection point, we're looking for light green equals purple. Haha. This one without making mistakes, I'm going to get x equals 19. Okay. That means that this is 19 something. So that means by default, that second point, I have to say it equals 16. follow sometimes when like I'm actually doing the thinking on the spot and can't find my mistakes. Are there any questions about how we got those 3 x values? Well, we're not ignoring it. I think this is a really good discussion. If this is 1, this is 19, then this one has to be 16, right? It can't be 25. But like, why would we get 2 answers? We see that green and the green only cross 1 time. So here's why. But I squared it, which means I created a situation where I was going to have a second solution. Solution that, what is that called? If you've heard the word extraneous, it doesn't actually, like if 25 and into the original equation, third of 25 is 5. However, 20 minus 25 is negative. So 25 is considered an extraneous solution, like we fit this particular equation. It fit our modified equation where we squared everything, but that moment we squared, we introduced for a term that actually work in the original. Okay, so let's put X through that one so we don't get confused. This is extraneous solution. Okay. All right. Now, all of this is to say that we can now set up and solve our integral. Right. And as I said earlier, we are going to split our integral, write 2 integrals. We're going to have the area to this red line, and then we'll have the area to the right of this red line. Okay. For the area on this side, we'll do top minus bottom, but it's going to be dark green minus purple first. So my area will equal the integral from 1 to 16 of dark green minus purple. Okay. And again, the integral root will find this little, to find the root of, yeah, I'm going to go from 16 to 19 of light green minus purple. So let me just pause here for a moment because I think this is a really important concept. That when we say top minus bottom, it always has to be the same top function. It always has to be the bottom function. As soon as that switches, one option is to split into different integrals. Okay. Now, I said one, probably a little nervous when I say one option. That means that there's another option, and sometimes I really like having more than one option. Okay. But here's what we're gonna do. We're gonna grab this diagram. We're gonna treat. Well, I'm gonna treat. Just click and get down here, and I'm gonna zoom in. I'm going to say, what if? One of my favorite mathematical games. What if I didn't want two intervals? What if I changed the way I drew the rectangle? Okay. What if I drew my rectangles this way? If I draw my rectangles this way, what am I asking to do? Exactly. This diagram is saying use dy. And how do we know? Because our rectangles are stacking up. We have the light green curve always on the right-hand side, and we have the dark green curve that is always on the left-hand. I only need one integral if I do it. Okay. Now, if we wanted to set this up, I would need the integral from C to D of my right curve minus the left. Okay. I bet you know what the C is. This is my C value. This is where I'm going to start counting. And I'm going to count all the way until I get up to here, which is going to be like the tiniest rectangle. I can fill in the 1. My right curve is the 20 minus x. My left curve is the square root of x. And I have a dy. Oh, it makes me uncomfortable even looking at it. Okay. Makes me uncomfortable because I've got x's and y's all mixed together, and I know I can't do that. But to find this top number, we can, exactly as Lucas said, we need this 16. We can plug it into either the dark green or the light green equation. Either way, when we plug it in, we should get 4. Okay. I have to change 2 things though. I have to take minus x. I have to change it into an equation with y. So the original equation was y equals 20 minus x. How do I get x all by itself? Well, I do a little arithmetic and I get x equals 20 minus y. This is what I'm going to put in place of this. I want to change it to be an equation with y's, so it matches with my y bounds and my dy. Similarly, this was the dark green equation. And if I get x by itself, I'll get x equals y squared. This will be what I put in place of this. And so let's see what we get. The integral from 1 to 4 of 20 minus y squared dy. Okay. By looking at this from a different perspective, I was able to, and this does not happen all the time, but I was able to create a situation where at the end, I only have one integral. And for each of the terms, I only need power. Compare it to this one. I have this is a square root. I've got bigger numbers. So if I were computing it by hand, the dx would work, but it might take a little bit longer. Okay. Whereas the dy, I think in this case, I would argue a bit more efficient because we get nicer values to work with, all right? The moral of this story is that we can use dx in certain cases. That will be the best option. In other cases, we would want to use dy because that is clearly the better option, like example number 8. But there's some that really are in this like in-between land where you could go either, and that's okay. How are we feeling about this last example, example 6? Okay, that is fair. That is fair. So my challenge to you this weekend, knowing that next week we're going to take all this 2-dimensional stuff and turn it into 3 dimensions, is to spend some time working on solving some more of these problems. And in particular, drawing a diagram, finding the intersections, and evaluating the input. Right? I'm going to give some answers so that you'll have something to check. But this is a case where the best way to set yourself up for success is to grind through the problems. I know that doesn't sound fun, but there is not really a shortcut in terms of getting it. The concept here, really have to kind of marinate on it, practice your setups, see like what would work for you.
Do you have any videos for these problems from last semester?
I do not know.
Okay, thank you.
Okay. All right. I am, however, available if you have specific. So folks, if you have questions that are not just, is this right? Okay, there's not a lot I can do. If you say, is this right? I could say, no, and that's it. That's the end of the conversation. So practice asking questions that are more what you're asking for. Like, are you worried about your setup? Are you worried about your finding your interest? Where is it that you're really finding that challenge? Okay. And that is something, that is a skill that is maybe not a mathematical skill, like content wise, but that ability to ask a quote unquote good question, a question that gets you the answers you want, is definitely something that we can all work on. Okay. I'm going to go ahead and post these notes, and they'll be posted in class. So you should have access. Okay. And then you can start working on those. All right, so folks, we're going to go ahead and stop the video here.